Hello everyone, in this video we'll be discussing about hemostasis. What is hemostasis? Hemostasis is the process of arresting of bleeding with the formation of a definitive clot. So when bleeding occurs in any part of the body, the processes which are activated to arrest that bleeding, and we all know that bleeding is arrested by the formation of a clot. So that entire process from the starting of bleeding till the formation of a clot is what is known as hemostasis. And there are actually two parts or two steps. The first part is called as the primary hemostasis, which is activated immediately after the arrest of bleeding, and this is a function of the platelets. So platelets are involved in the primary hemostasis, and once the primary hemostasis occurs, then the secondary hemostasis follows it, and by the end of secondary hemostasis you have a definitive clot. The secondary hemostasis is mediated by the clotting factors. Why is this important? Well, the reason is that if there is a deficiency of platelets or disorders involving the platelets, it will affect the primary hemostasis, whereas if there are clotting factor abnormality, that will affect the secondary hemostasis, and they give rise to different kinds of bleeding disorders. Having said that, we now move on to the primary hemostasis, and as I have said, it extends from the starting of bleeding till the formation of a platelet plug. So a platelet plug is formed to temporarily stop the bleeding, or it's kind of like a temporary clot which has to be converted into a definitive clot by the action of secondary hemostasis. So to understand the mechanism behind the primary hemostasis, we first have to understand about the platelets. So here I have a platelet. The peculiarity of platelet is that it is actually an anucleate cell. It does not have a nucleus. In fact, it is actually formed by a large cell called as megakaryocyte, which is a precursor. And this large megakaryocyte, the cytoplasm of one megakaryocyte, will pinch out and give out several thousands of platelets. So it does not have a nucleus. Now we have to know about two important receptors on the surface of platelets. The first one is a glycoprotein 1b receptor, and the second one is the glycoprotein 2b or 3a receptors, and these two receptors are involved in the primary hemostasis. Inside the platelets, we have two granules. The one marked here in yellow is the alpha granule, and the other one is the dense granule. And these granules store different materials and molecules inside them which are essential for primary hemostasis, and we'll discuss about that. So what happens when an injury occurs? So here I have drawn the endothelium. And when an injury occurs, or when there is an injury to the blood vessels, obviously the endothelial layer will get broken down, as I have shown in this region. And below the endothelium, just below the endothelium, we have subendothelial collagen fibers. And these subendothelial collagen fibers are important in hemostasis because normally, because of the presence of an intact endothelium, the factors that promote hemostasis, which are present in the plasma and the endothelium, do not come in contact with the subendothelial collagen. However, when an injury occurs or when the endothelial layer is broken down, this subendothelial collagen is exposed, and as a result, inside the alpha granules of platelets, there is a molecule called as von Willebrand factor, that is VWF. This factor is present first in platelets, and secondly, it's also present in the endothelial cells. So when an injury occurs to the endothelium, the von Willebrand factor will get released, and this von Willebrand factor will get attached to the broken endothelium. So the von Willebrand factor will attach to the broken endothelium, and the von Willebrand factor will attract the platelets through the GP1B receptor, which we have mentioned here. This is the GP1B receptor. So the GP1B receptor will link with the von Willebrand factor, which is attached to the subendothelial collagen. And as a result, what happens? This leads to the platelet, or this leads to the beginning of platelet adhesion. So the first step is when a blood vessel injury occurs, immediately there is actually one step, that is a vasoconstriction of blood vessels. So immediately the blood vessels will constrict. It's due to reflex mechanism. And then what happens is that the second one is that the von Willebrand factor will bind to the subendothelial collagen, and the third step is platelet adhesion. Once the platelet is adheres to the von Willebrand factor, the platelets undergoes activation, and after activation, the activated platelets will secrete its granules. So the contents of the alpha and dense granules are secreted out. So what are those contents? In alpha granules, we have the von Willebrand factor, which is again released by the platelets, which will bind to the expose subendothelial collagen, which will attract more platelets, and the process will go on like a cycle. Apart from that, we have the fibronectin, we have platelet activating factors, and so on. And in the dense granules, we have ADP, we have serotonin, thromboxane A2, and so on. Now, what happens when these molecules are secreted? Well, they will activate the surrounding platelets, and these surrounding platelets will then start to aggregate with each other. And how do these platelets aggregate? For example, the one of the molecules released is ADP. The ADP will activate the surrounding platelets. So all of these platelets which are present in the plasma get activated, and these platelets will now start linking with each other. Now the question is, how do these platelets link with each other? That is where the second receptor comes to play, that is the GP2B3A receptor present in the platelets. Now this receptor, they do not directly bind to the other platelets, but however what happens is that the GP glycoprotein 2B3A receptor will first bind to fibrinogen, and this fibrinogen will bind to the other GP2B3A receptor present on the next platelet molecule. So fibrinogen will act as the linking molecule, which will lead to the fifth and final step in primary hemostasis, that is platelet aggregation. With that, we form a temporary clot. So to write it once again in a more beautiful way, so when we have an injury to the endothelium, there will be release of von Willebrand factor, and the von Willebrand factor will bind to the subendothelial collagen, and as a result what happens is that through the GP1B receptor, the platelet will bind to the von Willebrand factor, and this will lead to platelet activation followed by secretion, activation, adhesion followed by secretion, and the secreted products lead to platelet aggregation. And after the platelet aggregation, we have finally formed a temporary clot, or a platelet plug formation has occurred. This concludes the primary hemostasis. However, this is just a weak clot. This is not enough. We have to form a definitive clot, and the definitive clot is formed by fibrin molecule. So that is formed by the action of secondary mediators, or by secondary hemostasis by the action of clotting factors. And the process starting from the primary platelet plug formation till the end of formation of a definitive clot or a fibrin clot is known as secondary hemostasis. So what happens? Before that, we need to know that they are mediated by the clotting factors, and this occurs by two mechanisms. So there is an intrinsic pathway, and then there is an extrinsic pathway, and different clotting factors are involved. What we need to know is that there are actually 13 clotting factors, and depending upon the clotting factors which are involved, we have an intrinsic pathway and an extrinsic pathway. The extrinsic pathway is activated when there is trauma to the endothelium, or when there is an injury to the endothelium. Intrinsic pathway occurs when the blood comes in contact with a negatively charged particle such as silica, or in other words, if you place a blood in a test tube, or when you take it out of the body, the intrinsic pathway gets activated. So when blood comes in contact with a negatively charged particle like silica, the intrinsic pathway is activated. Now, depending on whichever pathway is activated, ultimately both of these pathways will have some common grounds, that is, the different clotting factors are involved, which we will talk about next. And then these clotting factors ultimately they will lead to the activation of factor 10A. So factor 10, clotting factor 10 will be activated, and the clotting factor 10 will then convert prothrombin to its active form known as thrombin. So there is a formation of thrombin, and this thrombin will convert fibrinogen, which is the inactive form, into fibrin, and the fibrin will then form the clot or the definitive clot. This is the step which are occurring in the secondary hemostasis. Now we need to know which are the clotting factors that are involved in intrinsic pathway and which are the clotting factors which are involved in extrinsic pathway. So let's move to that. In intrinsic pathway, the code is 10. 10 is how you remember the clotting factors which are involved. So let's get to that. The first one is the factor 12. So T stands for the beginning of the word 12. So factor 12 gets converted into its active form, which is depicted by A, that is factor 12A, and this requires low molecular weight kininogens. And after factor 12A is activated, what happens is that this factor 12A that will convert factor 11. E stands for 11. So it will convert factor 11 into its active form, that is 11A. And what does factor 11A do? Well, the factor 11A in the intrinsic pathway that will then convert. This occurs as a cascade or a series of steps. That is why this is also known as a coagulation cascade, because you need each of these clotting factors and they work in an order, in a stepwise manner. One activates the other and the cycle goes on. So the factor 11A or the activated factor 11 will then convert the factor 9 into its active form, that is activated factor 9. Activated factor 9 will convert what we have said earlier, that is factor 10 will be converted to activated factor 10A. And this step involves another factor, that is the factor 8. So factor 8 is involved in this step. Now the peculiarity of factor 8 is that the factor 8 is not working alone. The factor 8 will instead form a complex with von Willebrand factor, which we have mentioned earlier, that is VWF. So these two complexes are also involved in the activation of factor 10 to factor 10A. So this is about the intrinsic pathway, and then we have the other common pathway which we have said earlier, that is the activation of thrombin, then the activation of fibrin, which we'll get to that. Before that, we need to now discuss about the extrinsic pathway. So which are the clotting factors involved in the extrinsic pathway? I have said earlier that extrinsic pathway is formed or activated by trauma or injury to the endothelium. The reason is that when the endothelium is injured, tissue factor is activated, or which we write in short form as TF. TF is actually, it is the factor 3. The other name for factor 3 is tissue factor, and this tissue factor 3 or thromboplastin, which is another name, that will combine with factor 7. So factor 3 or tissue factor or thromboplastin will combine with factor 7 and they will form a complex, that is the TF7 complex, and this complex will then convert factor 10 into its activated form. So this is the difference in extrinsic pathway when compared to the intrinsic pathway. So the code for intrinsic pathway is 10, whereas the code for the extrinsic pathway, to remember it, you can remember it as 3 plus 7 is equal to 10. That is factor 3 plus factor 7 will finally activate the factor 10. Now the activated factor 10A, ultimately, now we enter the common ground. What they do is that they will convert the inactive prothrombin molecule into the active thrombin molecule. And this active thrombin molecule, this requires a complex. So 10A converts prothrombin with the help of a complex, and this process involves or requires calcium as a cofactor. It requires the membrane phospholipids. It also requires activated factor 5A. So this is a complex which is required for the activation of thrombin. Now what does the thrombin do? The thrombin will then activate what we have said earlier, that is the fibrinogen, into fibrin. Now this fibrin is in the monomer form, and this fibrin must link with each other into a polymer form, and that is what forms the definitive clot. It's a fibrin meshwork formed by fibrin polymers. Now the conversion of fibrin monomer into fibrin polymer requires the factor 13. So now we see how many clotting factors are actually required for the coagulation cascade, and it might feel overwhelming. That is why all we need to remember is that for the intrinsic pathway we have the 10, for the extrinsic pathway we have 3 plus 7 is equal to 10. Then for fibrinogen polymerization we require factor 13A. So these are the factors which are involved in the coagulation cascade. So that's how we form a definite clot. Definite clot is formed. Now the polymerized fibrin molecules, they will cross link with each other with the help of collagen, and that link is stabilized by what we have said earlier, that is a factor 13A. So this leads to the formation of a definitive clot and the bleeding is arrested. Now, having said all of this, we now have the next question. What happens to the clot? Does this clot stay in the body forever? No, this clot must be lysed down and broken down, because otherwise, imagine if this is our blood vessel and we have a large clot over this which stays like it is. What will happen is that it will lead to the formation of a thrombus. The blood flow will be turbulent and it will lead to a lot of complications. As a result, our body will immediately try and remove this clot once the bleeding has arrested. And this is due to the action of the fibrinolytic system. So the fibrinolytic system is responsible for lysing the definitive clot. So that is a function of fibrinolytic system. So what are the components of this fibrinolytic system? So we'll get to that. It begins with plasminogen, which is an inactive molecule secreted by the liver. And this plasminogen is converted into its active form, which is plasmin. And who converts it? It is converted by two molecules. That is, first one is tissue plasminogen activator, or the other enzyme is urokinase. Now this is exactly the level or the pathway where the streptokinase, which we all know, streptokinase is a drug which is given for patients with myocardial infarction or stroke. The reason is that if there is an MI or a stroke, there is clot formation in the vasculature of the heart or the central nervous system, and these clots are lysed by streptokinase. And the mechanism of action is that streptokinase will activate the conversion of plasminogen to plasmin, and plasmin will then lyse the clots, and as a result the blood clots formed in these vessels are broken down. So that's the mechanism of streptokinase. Now this plasmin which is formed, this plasmin will act on the fibrin meshwork, which we have said, the fibrin polymers and the fibrin meshwork, and they will degrade the fibrin to produce the fibrin derived or fibrin degradation products, which is written in short form as FDP. Along with that, it will also form D dimers. The D dimers are actually the molecular products which are formed when the fibrin is degraded. And to understand that, we'll have to go really deep into the structure of the fibrin molecule, which is not necessary. So that's about the fibrinolytic system. So now we have learned what happens when a bleeding starts and how a temporary clot is first formed. Then it is converted into a secondary clot by the secondary hemostasis, by the action of clotting factors, and how the clots are then lysed by the fibrinolytic system. Now finally we'll end this session with anticoagulants which are present in our body. So far we have been talking about how coagulation has occurred, right? And how they're broken down. Now there are some anticoagulants in our body, and these anticoagulants, the molecules involved include: one is antithrombin 3. As the name suggests, it has an activity which inhibits thrombin. Then we have protein C, we have protein S. So these are some of the anticoagulants. Now how do they all work? Let's see. In our body, the thrombin that is formed by the activation of prothrombin, that will actually bind to a molecule called as thrombomodulin. So the thrombin and thrombomodulin will form a complex, and this thrombin and thrombomodulin, that is responsible for activating protein C. So the inactivated protein C will become activated protein C, and this protein C, which is activated along with the protein S, they will inhibit or they will inactivate factor 5 and factor 8. So that is their anticoagulant effect. Now where are factor 5 and factor 8A present? So let's go back to the pathway. Here we see that factor 8 is present in the formation of factor 10A, and factor 5 activated is formed in the formation of thrombin. So these are the two levels where our protein C and protein S act, by the activation of thrombin thrombomodulin. Another compound which we have is the antithrombin 3. This antithrombin 3, as the name suggests, it will inhibit thrombin, and along with thrombin it will also inhibit some of the other clotting factors such as activated 10A, 11A, 12A, and 9A and 7A. What we find is that the 12, 11, 9 are inhibited, which means that the intrinsic pathway is involved. Along with that, 10A and 7A are also inhibited. So that's about anticoagulants, and that's about hemostasis in this video.